Hi, I'm Donna Perigin, and I teach chemistry at Jacksonville State University, which is a small university in northeast Alabama. So the question has been brought up in quite a few forums that I've been on. Can bottles of salt water, capped bottles of concentrated salt water floating in a water trough, keep the water trough from freezing? I'm sorry, I didn't mean to say from melting here. I meant to say from freezing. So freezing. Okay? So someone even said that if you were a simple high school chemistry student, that you could figure this out. This would be an easy problem for you, that it actually isn't going to work. Okay? Well, the answer is it can work under certain circumstances. So it might work for you and it might not work for you. And we can actually do a little bit of math to find out. Now, this is not a problem that I would give to my Gen Chem students. This is a problem I would give to my more advanced physical chemistry students, which I don't even actually teach physical chemistry, but we would give this type of problem to a non-calculus based physical chemistry type student. It isn't an extremely difficult problem, but it's something that I would consider to be an advanced challenge problem for a Gen Chem student. This is not a simple problem, but anyway, it can be worked relatively straightforward with a relatively straightforward approach. And so here's how we can actually do that. We can calculate first the moles of sodium chloride required to make a 1 liter saturated sodium chloride solution. Okay, so I'm going to assume we have 1 liter of saturated sodium chloride solution in our jug. And the other thing I can do from that is I can make a conversion factor and see how much ice I can melt with 1 liter of saturated salt solution. Okay. And then I can calculate the molality of that solution. Okay, and then calculate the freezing point depression of this solution. So in other words, at what temperature will this freeze? Calculate how many moles of heat this solution can absorb. Calculate the amount of heat in joules that this solution can absorb, and then calculate how much ice it can melt. So that's the way we're going to have to do this. And so in the end, we can figure out how much ice a 1 liter bottle can melt. And we have to understand something else here, and that is if you have ice in water, like if you have a glass of ice water, okay, that ice water is going to exist at 0 degrees C, which is 32 degrees Fahrenheit, okay? Now, if you have ice in your water trough, you're going to have a layer of ice on top, and that ice on top is in contact with the outside air, so it could actually be colder than the, say a glass of ice water, okay? So, don't depend on this information to go off for the weekend and figure that your animals are going to be okay. You need to check on your animals. If you're in freezing conditions, you need to be checking on them every couple of hours. I'm just working an interesting math problem here. It's not for you to use for determining how many bottles of water you need to put in your animal trough to keep it from melting, okay? But the fact is, you can melt a little ice from your animal trough by putting jugs of salt water in there, but it's going to kind of depend on how effective it is. It's going to depend on what area of the country you live in, and it may work for you depending on if you're in an area where you get just a little skim of ice on top of your water trough, okay? But don't depend on this and go off and leave your animals in a situation where they cannot get water. I don't want to be responsible for that. But what we do need to understand is how a heating curve works before we begin to work this problem. And that is, if you are below 0 degrees C, which is 32 degrees Fahrenheit, so right here on this heating curve, if you're below that point, then you're going to have solid ice. So that would be if you're if your water trough is completely frozen solid, and that's not what this problem is for. We're going to assume that your water trough still has some water in it and that it is approximately 0 degrees C. We have to make that assumption in order to work this problem. So if you're down here below the freezing point of water, then that's going to be governed by the equation. The amount of heat it's going to take to warm it is going to be equal to the mass of the water that you have, and we go with grams on that, times your C sub S for ice, okay, and that you can look up, that is the heat capacity for ice, and you can look up some different equations, different videos on heat capacity. I'm not going to explain what heat capacity is here, times the change in temperature. Okay, so that would be governed in this region. We're not going to be working that problem. Okay, so then as you reach the point where your ice begins to melt, you're at 0 degrees C. Okay, so now the heat required to melt that ice is going to be dependent on the mass of ice in grams times the heat of fusion. Okay, and that heat of fusion is a constant that you can look up. We're going to be using that constant. Okay, and then as you warm again, okay, from as once all your ice melts and you're in the liquid region, then your Q is going to be dependent on your mass times the C sub S for water, not ice, times the change in temperature. And then as you boil your water, you're going to have Q is equal to the mass times the heat of vaporization and that sort of thing. Okay, so the reason that we don't have delta T here in this region at 0 degrees C is because the temperature doesn't change as the ice melts. We're going to stay at 0. So if you're assuming that you have some water in your water trough, and then we can assume that that water is at 0, that water ice equilibrium is at 0 degrees C. Now it really isn't probably going to be the case, because above your water trough your air may be extremely cold and that ice may be below 0, but we have to make that assumption in order to work this problem. Okay, so we're going to start again by calculating the moles of sodium chloride to make a 1 liter saturated sodium chloride solution. That means we have as much salt as that 1 liter of water can hold. And if you look up the solubility of salt in water, you'll see that 1 liter of water can hold 360 grams of sodium chloride. Okay, so let's start with that. 360 grams of sodium chloride. Now if you need to, you can convert that to pounds. I didn't do that for you, or ounces. Okay, and so you can just look that up, put 360 grams into a converter on the internet, convert that to pounds. Okay, so 1 mole, okay, is 58.443 grams, and I got that from the periodic table. Okay, all right, and so that gives us 6.16 moles of sodium chloride per 1 liter of water. Okay, it will dissolve in 1 liter of water. Let me just say that. And so remember that sodium chloride dissociates, NaCl dissociates into Na plus Cl minus, and that means for every 1 mole of sodium chloride, I get 2 moles of ions. And that's what matters when we're talking about colligative properties, is that we have ions, okay? So I need to take my 6.16 and multiply that times 2. Okay, and so I'll have 12.32 moles of ions in my 1 liter of solution. Okay, so I also know that 1 gram of water, 1 milliliter of water weighs 1 gram. So the density of water is 1 gram per milliliter. So therefore, 1,000 grams of water is 1,000 milliliters, and 1,000 grams is 1 kilogram. So 1 kilogram of water is 1 liter of water. Okay, so what I need to calculate the freezing point in depression is not molarity even, I need molality. And molality is defined as moles of solute, and in this case we're going to use our ions, per kilogram of solvent. Okay, and so I know that I have 12.32 moles of ions, and I know that, so let's write that down, 12.32 moles of ions in my 1 liter of water. Okay, and so I also know that 1 liter of water weighs 1 kilogram, so that is 12.32 moles per kilogram. And I'm doing this kind of approximate. I'm not going to be watching sig figs real close, and so that is 12.32 molal, which is represented by a little m. Okay, so now we know the molality of a concentrated, saturated sodium chloride solution, which means that that's all the salt that this can hold. If you've got salt that is dissolved on the, that is crashed out on the bottom of your solution, that would be a saturated solution. You need to put so much salt in there that it can no longer hold any more salt. Okay? Now the next thing we need to do is calculate the freezing point depression. In other words, at what temperature will this bottle of salt water freeze? In other words, at what temperature will my liter bottle of salt water begin to freeze? And I can actually calculate that. So the delta T sub F, or the freezing point depression, the change in temperature that's required to freeze this water from 0 degrees, is equal to the molal concentration of the water times the K sub F, or the freezing point depression constant for water. Okay, and so that's going to be, we had 12.32 molal times 1.86 degrees C per molal. Okay, and that cancels, and so we get 22.92 degrees C. That's our delta T. That's our change in temperature. So the normal freezing point for water is 0 degrees C. So I need to subtract that 22.92 degrees C from that, and that's going to give me negative 22.92 degrees C, and that's my freezing point for my saltwater solution. Okay, so that 1 liter of salt water with 360 grams or more of salt, because that's all it can dissolve. Was that 360 grams? Yeah, 360 grams. It won't freeze until I get to negative 22.92 degrees C. That's why you put salt in on the roads or on your porch. But if you get down to less than negative 23 degrees C, even the salt's not going to be able to keep your roads from freezing, okay? Because that's a saturated saltwater solution. All right, now the next thing we need to calculate is the heat required to reach that freezing point, or in other words, how much heat can this water absorb before it freezes. Okay, and so we're still in the liquid phase of our saltwater solution, so that's going to be governed by our Q, and I'm going to call this Q1, equal to the mass of the water times the C sub S for water times delta T. Okay, so that's going to be equal to 1,000 grams times, that's 1,000 here, 4.184 joules per gram degrees C times 22.92 degrees C. In other words, we need to be lowered by that amount. I put that down here, okay? So my delta T my change in temperature needs to be 22.92 degrees C before it can freeze. So it needs to absorb 95,897.28 joules of heat before it will freeze. Okay, so we know how much heat it can absorb before it freezes, that liter of water, okay, which sounds like a lot. But we don't really know how much that is. We don't have a real tangible understanding of how much heat that is. So let's calculate how much ice that heat can melt. I mean, that water can melt before it freezes. Okay, so what I want to say is our Q1 is equal to, in joules, is equal to the mass of our water, of the mass of ice that it can melt times the heat of fusion for ice. Okay, so we want to know, we know what our Q is, and we know what the heat of fusion is because that's a constant, okay? So we can calculate the mass of ice that this much heat can melt. So what I'm saying is, okay, I've got these bottles of water floating in my ice trough, okay? And I've got a little thin layer of ice on top here. How much ice can these bottles melt before they begin to freeze themselves? Okay, and that's what I'm calculating here. So Q is equal to mass in grams times the heat of fusion. So mass in grams is equal to Q over the heat of fusion, which is equal to, our Q was 95897.28 joules divided by the heat of fusion for ice, which is 334 joules per gram. Okay, and that's equal to 287.11 grams of ice. Okay, grams of ice. So 1 liter, so what we're saying here is 1 liter of water of saturated, let me rewrite that. Saturated salt water in a bottle separated from the ice can melt about 300 grams of ice in the trough. Okay, which isn't a lot. So it can melt about 1/3 of its volume in ice. Okay, so basically what we're saying here, if you had a gallon jug or a 4-liter jug of saturated saltwater solution, that could melt, so let's say 1 gallon or 4 liters could melt about 1148.44 grams of ice. Okay, so indeed, that you see, like if you had a little skim of ice here, you could melt a little ice off the top of your trough if you keep some bottles of salt water in there. I mean, obviously you wouldn't want to put salt in your feeder because your animals can't drink that, but I'm talking about bottled salt water floating in your water trough. You could, in fact, keep a little skim of ice off the top. Now, if this ice is too thick, you're going to exceed this 1,200 grams per gallon. So we could use that as a conversion factor. 1 gallon of salt water, saturated salt water solution, can melt 1,200 grams of ice. And you could go to a converting site and figure out how much that is. Let's say 1,200 grams of ice to let's say to pounds. I didn't have a conversion. 1,200 grams is about 2.5 pounds. Okay, so 1 gallon, let's see, where was I at? So 1 gallon of salt water floating in your in your trough can melt about 2.5 pounds of ice, which is quite a bit. But think about it like this: the colder that water gets, it's not going to be able to do that for long. Okay, so it's going to depend on a whole lot of factors. So I certainly don't want you to say, hey, she said my water is not going to freeze up. I'm not saying that at all. All I'm saying is there's a little bit of validity to this, and somebody might find it useful if they're in an area where the water freezes every now and then, but not all the time. They might find this actually a useful technique. So you can prove this mathematically, and I just wanted to go ahead and do that just as kind of a fun exercise. Thanks.